Beyond the stars, deep in the cosmos, there is a world about 146 light-years away from us. Its name is HD 137010b. And the story of this world is not just the story of a planetary discovery. This is the story of how human curiosity, technology, and the power of community come together to illuminate the secrets of the universe. If you are subscribed, we can begin to talk about the possibilities, the evidence, and what might be for this Earth-like planet. The year is 2017. NASA's Kepler Space Telescope had been traveling through space for 8 years, but by then it was moving forward, aged and exhausted. 2 reaction wheels were malfunctioning. For everyone, the mission seemed to be over. But within Kepler's data archives, countless secrets yet to be discovered were hidden. The story of HD 137010b begins with exactly such a secret, data collected 8 years earlier and left waiting in digital darkness for years. This planet orbits a star astronomers call a K-dwarf or K-type dwarf. This star, known as HD 137010, resembles our Sun but is also different. It is approximately 1,000 degrees cooler, slightly smaller, slightly dimmer, with its orange glow like a fire flickering in the silence of the night. These stars are actually among the most interesting stars in the universe. Why? Because they can live for billions of years. While the lifespan of our Sun is around 10 billion years, K-dwarf stars can shine for 50, 60, even 70 billion years. This duration is so long that the universe itself is estimated to be only 13.8 billion years old, which means none of these stars has died yet. All of them are still in their youthful stage. So why are these K-dwarf stars so important? Because they can offer a perfect environment for life. M-dwarf stars, being very small and cool, require planets in the habitable zone to orbit very close to the star. And this proximity can cause the star's powerful solar flares to strip away planetary atmospheres. On the other hand, G-class stars like our Sun are shorter-lived, but K-dwarf stars? Right in the middle. They live long enough for life to have time to evolve. They are mild enough that they do not scorch their planets. And this is where HD 137010b comes in, orbiting such a star. The planet itself is almost the same size as Earth, only 6% larger, and its orbit? 355 days. 1 year on Earth is 365 days, just a 10-day difference. Is this a coincidence? No. This tells us that the distance between the planet and its star is almost the same as the distance between Earth and the Sun. But here is the problem. Because the HD 137010 star is cooler than our Sun, the heat and light the planet receives are only 1/3 of what Earth receives. Scientists calculated, and the resulting number is freezing. -70 degrees Celsius. Some estimates even drop to -90 degrees. Mars's average surface temperature is around -65 degrees, so HD 137010b appears even colder than Mars. Now imagine yourself on this world. You look up at the sky and there is an orange star. It does not look as large as our Sun, but it is still impressive. But no matter how long you look, you cannot warm up, because this world is in a state of deep freezing. The surface is frozen over. If there is an atmosphere, it has to be extremely thick and likely rich in carbon dioxide so that liquid water can exist at such a distant location. However, scientists estimate the probability of this planet being in the habitable zone as 50%. How can this be? Because what we call the habitable zone is a flexible concept. With a conservative definition, the planet lies at the outer edge of this zone, perhaps even slightly outside it. But if we use the definition of an optimistic habitable zone, the planet could be right in the middle of it. What if the atmosphere of HD 137010b is different from Earth's? What if the amount of carbon dioxide is much higher? Then the greenhouse effect would be much stronger and the planet could warm up. Perhaps the surface temperature could rise above zero. Perhaps oceans could form. Perhaps the expected life could emerge. Or perhaps this planet is completely a frozen world. Scientists call this the snowball Earth scenario. Deep in history, billions of years ago, Earth itself also experienced such frozen periods. During a period known as the Huronian Ice Age, Earth was almost entirely covered in ice, but life still continued. In the depths of the oceans, beneath the ice, microscopic organisms survived, and eventually, volcanic activity pumped carbon dioxide into the atmosphere, the greenhouse effect increased, and the ice age came to an end. So, is HD 137010b also experiencing such a turning point? Or will it remain a frozen world forever? We do not know. We do not know yet because this planet has been observed only once. Only a single transit, that is, the planet passing in front of its star, was detected. And this transit occurred in 2017 during the 15th campaign of Kepler's K2 mission. Now, let me tell you the story of that campaign. The Kepler Space Telescope experienced a serious failure in 2013. 2 of its 4 reaction wheels failed. These wheels were used to keep the telescope stable in space. With 2 wheels, remaining perfectly stable was impossible. NASA engineers found a solution, using the solar wind. Like a skier balancing their body to stand against a current, they began to balance Kepler using the pressure of sunlight. But this came at a cost. The telescope could no longer continuously observe the same location. Every 3 months, it had to turn toward a new region. This new operational model was called K2. In August of 2017, K2's 15th campaign began. Target: the Scorpius constellation region. NASA selected 23,279 long cadence targets and 119 short cadence targets. Among these targets were young stars, variable stars, binary star systems, and even asteroids and comets. And HD 137010 was also somewhere on this list. A modest K-dwarf star. Not bright, not famous, just one of millions of stars. The 15th campaign lasted 88 days, from August 23rd to November 20th. During this time, Kepler took an image every 30 minutes. In each image, the brightness of thousands of stars was recorded. These data were sent to Earth and added to the archives. And then, nothing happened for years. Because the Kepler data are so massive that even automated computer algorithms cannot process all of them. Some signals are very weak, some patterns are very complex, and this is where citizen science comes into play. The Planet Hunters project was launched in 2010. The idea was simple but revolutionary: to enable people, ordinary people, to work together with scientists. The team, led by Deborah Fisher from Yale University, opened the Kepler data to the public. On their website, thousands of light curves, graphs showing changes in a star's brightness over time, were uploaded. And people from around the world, ordinary people with no scientific background, began looking at these graphs. Why? Because the human brain is incredibly skilled at pattern recognition. Computer algorithms are mathematical, precise, but sometimes too precise. Small deviations, noise, unexpected patterns, they can overlook these. But when a human looks at a graph, they can intuitively sense that something is wrong or different. They may not be able to explain exactly why, but they can say, there is something strange here. And in this way, more than 300,000 volunteers over 8 years examined more than 20 million light curves, and they discovered hundreds of planet candidates. PH-1b, the first Planet Hunter's planet, was a world orbiting 4 stars. Scientists thought such a system should be unstable, but the volunteers found it, and it was real. The story of Alexander Venner also begins in this context. When he was a high school student, he joined the Planet Hunters project. While studying, in his spare time, sitting in front of his computer, he looked at stellar light curves. And this experience affected him so deeply that he studied astronomy. He earned a PhD. And years later, now as a professional researcher, he returned to the data he had examined back then. The 2017 data, K2 Campaign 15. And there, in the light curve of HD 137010, he saw a 10-hour dip, a very subtle dip. The star's brightness had decreased by only 225 parts per million. To grasp this, think of this, like a 1 million watt light bulb dimming by 225 watts. You wouldn't even notice it with the naked eye, but Kepler's sensitive sensors detected it. Venner and his team could not believe it at first. This cannot be real, they said. But they checked the data again and again. They examined archival images, radio velocity measurements, how fast the star wobbles in space were checked. Using Gaia satellite data, they analyzed the star's motion. Everything pointed to the same conclusion. This was a real planetary transit. But there was a problem. Only a single transit. In the scientific world, to confirm a planet, at least 3 transits are usually required, because a single event could be an accident, a technical malfunction, an asteroid passing by. But if it repeats 3 times, then it is certain. For HD 137010b, there were no 3 transits, only one, a 10-hour signal. And then Kepler looked elsewhere. The campaign ended, and the planet, if it truly is a planet, was never observed again. So how can we learn so much about a planet from a single transit? This is where mathematics and physics come into play. The transit duration, 10 hours, provides information about the planet's size and orbital speed. The depth of the brightness drop, those 225 ppm, provides information about the planet's size. Because the larger the planet, the more light it blocks while passing in front of the star. Scientists know the density of the star. They know its mass, they know its radius. With this information, they can calculate how long the shadow formed during the planet's transit in front of the star will last. And these calculations give them the chance to estimate the orbital period. The result? 355 days, plus or minus 200 days. Yes, the uncertainty is very large, but the most likely value is 355 days. And this places the planet at a distance similar to Earth's, approximately 0.88 astronomical units. 1 astronomical unit is the distance between Earth and the Sun. So this planet is slightly closer to its star than Earth is. But because the star is cooler, the energy the planet receives is much lower. Calculations show that HD 137010b receives only 29% of the solar energy that Earth receives, and that is why it is so cold. Now let's look at the big picture. Why is this planet so important? After all, thousands of exoplanets have been discovered. Why is HD 137010b special? There are several reasons. First, this is one of the first planet candidates observed that has an orbital period of around 1 year and is Earth-sized. Most discovered planets are either very large, giant gas planets we call hot Jupiters, or in very close orbits. those that orbit their stars in just a few days. But Earth-sized planets with a one-year orbit? These are very rare, because they are very difficult to detect. Think about it. If a planet orbits its star once a year, you need at least 1 year of observation to detect it. And if you want 3 transits, 3 years. But Kepler's primary mission lasted only 4 years, and each K2 campaign lasted only 80 days. Therefore, catching long-period planets is almost impossible. For HD 137010b, they were lucky. The transit happened at exactly the right time, in the middle of the campaign. If it had occurred a few weeks earlier or later, Kepler would have missed it, and we would never have known. The second reason, the star is bright enough and close enough. 146 light-years. This is very close on cosmic scales, and the star's visual brightness is 10.1, quite bright on an astronomical scale. What does this mean? It means next-generation telescopes can study this planet. The James Webb Space Telescope, the Nancy Grace Roman Space Telescope, the Habitable Worlds Observatory, to be launched in the future, these telescopes can study the atmosphere of HD 137010b. They can perform spectroscopy. Is there water vapor in the atmosphere? Is there oxygen? Is there methane? They can search for answers to these questions. And maybe, just maybe, they can perform direct imaging. They can see the planet separately from its star, because the star is bright enough and the planet is far enough away. The star's glare may not completely overwhelm the planet. The third reason is scientifically very important. This planet can help us understand worlds at the outer edge of the habitable zone. Scientists have long wondered, where exactly does the habitable zone end? How cold can a planet be and still host life? Even in the history of our Earth, there were ice ages, periods that were almost completely frozen, but life survived. In fact, some scientists think that these harsh conditions actually accelerated evolutionary development, because hardship triggers adaptation. Europa, Jupiter's moon, is completely covered in ice, but beneath the ice there is a liquid water ocean, and there could be life there. Enceladus, Saturn's moon, is the same way. Its surface is frozen, but its interior is liquid, and it sprays water into space from hydrothermal vents. This shows that there is geological activity, and geological activity can provide the chemical reactions necessary for life. So, is HD 137010b a world like this? A frozen surface but an active interior? Maybe subsurface oceans? Maybe geothermal heat? We don't know these yet, but we have the tools to find out, or we will soon. Now let me tell you more about the power of citizen science, because the story of HD 137010b is also the story of the power of the community. Alexander Venner joined Planet Hunters when he was a high school student, and he was just one of thousands. People from all over the world, teachers, doctors, engineers, artists, retirees, students, all came together to contribute to science. Some devoted a few minutes every day, during a coffee break, after dinner. Some worked for hours. They took notes, made comparisons, and discussed in forums. And this community didn't just process data. They learned from each other. They communicated with scientists. They wrote papers. The Planet Hunters project had discovered more than 100 planet candidates in 8 years. Most of these were planets that computer algorithms had missed because the signals were too weak or the patterns were too irregular. But the human eye caught them. And this wasn't limited to planets. Project participants discovered eclipsing binary systems, variable stars, and even exocomets, comets in other star systems. All of these were published in academic journals, and the participants, ordinary citizens, became co-authors of these papers. One example, Hans Schwengler, a Swiss citizen scientist, discovered 2 previously unknown planets around the known hot Jupiter planet called WASP 47b. One was super-Earth-sized and in an orbit of just 0.8 days, meaning incredibly close to its star. The other was Neptune-sized and in a 9-day orbit. This discovery revolutionized astronomy, because until then, it was thought that there could be no other planets near hot Jupiters. Migration theories considered this impossible, but Hans Schwengler found it and became a co-author of a paper. Similarly, Planet Hunter's TESS, the newest version, has so far identified more than 150 Community TESS Objects of Interest, or CTOI. 81 of these were promoted to official TESS Object of Interest status, and 15 are confirmed planets. What does this mean? It means that people who are not professional scientists can make real discoveries, and this democratizes science. Science is no longer done only in universities and laboratories. You can do it in your homes, in your living rooms, even with your mobile phone. And HD 137010b is exactly an example of this. A journey that began with the curiosity of a high school student, a search that lasted for years, and finally, in 2026, a discovery, a world, perhaps a world that harbors life, or perhaps a barren land frozen forever, but still a world. Now, let's look to the future. How can we better understand HD 137010b? There are a few ways. First, more transit observations. The planet has a 1-year orbit, meaning it passes in front of its star once every year. The James Webb Space Telescope or ground-based telescopes can catch these transits. If 3 transits are observed, the planet becomes confirmed, no longer a candidate, but a real planet. Second, spectroscopy. While the planet is transiting, part of the starlight passes through the planet's atmosphere, and this light is absorbed by the gases in the atmosphere. Each gas absorbs different wavelengths. Therefore, by analyzing the light, we can learn what is in the atmosphere. Is there water vapor, carbon dioxide, oxygen, methane? If oxygen and methane are found together, this is very important, because these two gases normally react and destroy each other. If both are present in the atmosphere, it means they are being continuously produced, and the most well-known source of production, life. Third, direct imaging. The future Habitable Worlds Observatory will specialize in this. With a special device called a coronagraph, it will block the star's light and see only the planet. This is incredibly difficult because the planet is billions of times fainter than the star. But the technology is improving, and perhaps in 10 or 15 years, we may see a real photograph of HD 137010b. Fourth, radio velocity measurements. Observing the star, because while the planet orbits the star also traces a small circle. The planet pulls on the star, and this pull slightly changes the star's speed. Sometimes it moves toward us, sometimes away from us. By measuring these speed changes, we can calculate the planet's mass, and mass tells us whether the planet is gaseous or rocky. Fifth, asteroseismology. Listening to the sound waves inside the star. Yes, stars produce sound. Of course, sound does not propagate in space, but we can detect vibrations on the star's surface through changes in light. These vibrations provide information about the star's internal structure, its age, chemical composition, rotation rate, and this information helps us understand how the planet formed and evolved. But what if there really is life? What should we expect? First of all, if there is life on HD 137010b, it would most likely be microbial life, bacteria, archaea, perhaps some simple single-celled organisms. Complex life, plants, animals, this world is probably too cold for that. But microorganisms? They are incredibly resilient. On Earth, there are organisms that live in extreme environments. We call them extremophiles. Bacteria living at -20 degrees, archaeal cells living above 100 degrees, organisms living in highly acidic waters under intense radiation, kilometers deep, in complete darkness. If there are subsurface oceans on HD 137010b, there could be hydrothermal vents at the bottom of those oceans, just like on Earth. And around these vents, microorganisms fed by chemical energy could live, without the need for sunlight. Only geothermal energy and chemical reactions. Or maybe, on the surface, within cracks in the ice layer, there are glacial lakes, like the subglacial lakes in Southeast Antarctica, isolated for millions of years, yet still hosting microbial life. By studying life in extreme environments, scientists try to predict possible life forms on exoplanets. We call this astrobiology. And HD 137010b could be a perfect laboratory for astrobiological research. But maybe there is no life. Maybe HD 137010b is just a frozen, lifeless mass of rock. That is important too, because it teaches us other things. For example, how cold can an Earth-sized planet be? How does an atmosphere develop? Can a frozen world warm over time? Earth itself was very different during the period of heavy bombardment. Asteroids and comets were constantly colliding. The atmosphere was toxic, the oceans were acidic. But over time, geological processes cleaned the atmosphere. The oceans became neutral, and life emerged. Maybe HD 137010b is currently going through a difficult period. But billions of years from now, which the lifespan of K-dwarf stars makes possible, conditions could change. The star could become slightly brighter. The planet could warm. The ice could melt, and the chance for life could emerge. Or the opposite. Maybe HD 137010b was once warm and habitable, but over time, the star cooled. The planet froze. The oceans turned to ice. And life, if it existed, retreated underground or disappeared entirely. Both scenarios are possible, and both teach us something about the dynamic nature of the universe. Planets are not static. They change over time. They evolve. And we, as observers looking from Earth, can capture only a single moment, a photograph, just one frame of a story spanning billions of years. The story of HD 137010b is also the story of human civilization. Centuries ago, when we looked at the sky, we saw only stars, points of light. Some we called planets, but those were the ones in our solar system: Mars, Jupiter, Saturn. But we could not even imagine that other stars might also have planets. In the 1990s, the first exoplanet was discovered, 51 Pegasi b, a hot Jupiter. And the scientific world was shocked because, according to theory, such a massive planet could not be so close to its star. But there it was, real. Since that day, more than 5,000 exoplanets have been confirmed, and tens of thousands of candidates are still waiting. Each one is a world, each one unique. Some are hot, some are cold, some are massive, some are small, some are rocky, some are gaseous, some are alone, some exist with twin planets. And now we know, in our galaxy, there are hundreds of billions of planets, perhaps trillions, and billions of them are in the habitable zone, Earth-like, with the potential for liquid water. What does this mean? That we are not alone? Maybe. Maybe somewhere in the universe, right now, another civilization is looking up at the sky. Another citizen scientist is examining the data from their own Kepler. And maybe they are discovering Earth. Look, they might say, there is a planet there, and maybe it harbors life. Or maybe we are alone. Maybe life is so rare that among trillions of planets, there is only us. That is a frightening thought, but at the same time, it places a great responsibility on us. Because if we are alone, then life, consciousness, art, science, love, all of these exist only in us, and protecting them is our duty. HD 13701001b reminds us of both possibilities. Maybe there is life there, maybe there isn't, but our search continues because we want to know the answer. Since the beginning of human history, we have asked the question, are we alone? And now, for the first time, we have more tools to answer this question. The next decade will be a golden age for astrobiology. James Webb has detected water vapor in an exoplanet atmosphere for the first time. The Roman Space Telescope will be launched into orbit. The Habitable Worlds Observatory is being designed. Giant ground-based telescopes, the Extremely Large Telescope, the Giant Magellan Telescope, the 30-meter telescope are being built, all with the same goal: to find habitable worlds and to find signs of life. HD 13701001b is part of this search. Maybe it won't be the planet that gives the first answer, but it is an important step because it shows us that even at the outer edges of the habitable zone, there are Earth-sized planets, and we can find them, we can study them, and maybe, just maybe, we can find evidence of life. Finally, I want to tell you this. This story is not over yet. HD 13701001b is still a candidate. More observations are needed to confirm it. And maybe those observations will show that it is not a planet. Maybe there will be another explanation, an asteroid, a technical error. Who knows? But that doesn't matter, because the search will continue. New telescopes will be launched, new data will be collected, new citizen scientists will join projects, and new discoveries will be made. Maybe 10 years from now, another high school student in another data set will find another planet. And that planet, maybe it will show signs of life. Maybe it will have oceans. Maybe a chlorophyll reflection will be detected, a sign of the presence of plants. Maybe oxygen and methane will be found together, definitive evidence of life. Or maybe it will just be another frozen world, another mysterious sphere. But still, it will contribute to our knowledge. Still, we will understand our place in the universe a little better. Because this is how science progresses, step by step, question by question, observation by observation. And every discovery, every small finding brings us a little closer to the big picture. Understanding the nature of the universe, grasping the origin of life, and maybe, one day, definitively answering the question, are we alone? HD 13701010b is a world beyond the stars. Frozen, maybe. Lifeless, maybe. But at the same time, full of hope. Because it shows us that the search is alive, curiosity continues, and the human mind, whether a professional scientist or a high school student, is still trying to unravel, to understand the secrets of the universe. And who knows, maybe you, among the people listening to this, maybe you too will one day discover a planet. Because now science is open to everyone. Data is free. Projects are online. And all you need is curiosity, time, and patience. Planet Hunter's TESS is still active. Every day, new light curves are uploaded. Thousands of stars are observed. And maybe in one of them, a planet that no one has noticed yet is hidden, waiting for us, waiting to be discovered. So, don't see this story as an ending, but as a beginning. The story of HD 137010b may also be creating new stories. In the face of the vastness of the universe, you may feel insignificant, but you are not. Every observation matters. Every discovery is valuable, and every human has the potential to contribute to science. HD 137010b may not give us an answer, but we will keep asking questions. Maybe 100 years from now, maybe 1,000 years from now, another civilization will visit HD 137010b. And who knows, maybe other civilizations will find us. For more videos like this, don't forget to subscribe and like. Good night.